Okay, this video goes over the inventory problems. Problems 2A, 3, 21A, and 36. Problem 2A is where they want you to use an ABC classification. So what we have to do is determine some type of value, and the value is the annual usage cost. And that is just the product of the unit cost times the usage per year. Then we want to take all this data and we want to sort on the usage cost from high to low. So this is definitely the most important item. That's clearly an A item. And then this one down here is clearly a C item because it's least important. The trick is, how do we decide what the break point is? So what we're going to do is, this is going to be the relative frequency. And you could show it as a percent. We'll show it as a percent. And we're going to take this number divided by the total of all these. And I'm going to show that as a percent. Now I'm going to copy this formula down, so I'm going to put some dollar signs. And then I'm going to come up with the cumulative relative frequency. First one is just this one. The next one is this plus this. So this builds on itself, where the total at the end, it's 100%. And what I'm going to do is have a rule, and these are a little bit of rule of thumbs, but what the book says is that your A items make up about 60% of the value. So I'm going to use these top three as A's, and after that we'll have B's. And your C items typically make up between 5 and 10%. So I'm going to, these will be B's, and then the rest of these will be C's. So I've got 3 A items, I've got 5 B's, I got a whole bunch of C's. You may have broken it different. You may have had one more A, you may have one less A, you may have had that as its only A, as the only. That's really up to you, as long as you have some rule that I can see how you made the decision. The critical component of this is that you've got a handful that make up to almost 58% of all the value. So you need to manage those differently than you manage these. You probably want to make sure you know how many you have. You want to have really good understanding, a real good supplier relationship with these. These items are called stock keeping units, or SKUs. So you're going to have in a industrial setting, you're going to have a lot more than 16. You're going to have thousands. So you need to decide which of the ones you're going to manage closely and which of the ones you're not going to manage closely. 13.3 is an economic order quantity. They're given these bags. There's the annual demand is 1,215 bags. The cost of carrying one bag for the year is $75. Someone has done the hard work for us and has determined that if we put a bag of flour on a shelf and it sits there for a year, because of the storage cost, the obsolescence cost, maybe being stolen, getting lost, the cost of capital, all of those says that it costs us $75 if we leave a bag on the shelf for a year. And then the cost of placing an order is $10. Every time we place an order, that's what the cost of the act of placing an order is. So based on these cost drivers, we can calculate the ELQ, which is the square root of the 2 times D times S divided by H. It happens to be a whole number. It will not always be a whole number, but it says we should order 18 bags every time we place an order. That's the order quantity. So the average inventory level is 9 bags. The orders per year is the 1,215 divided by 18. So we're going to order 68 times. This is almost a little over once a week. Or it's ordering more often than once a week. If you follow that rule, then your cost of holding is your carrying cost multiplied by the cost of carrying one bag for the year. Your cost of ordering is the number of orders times $10. They will always be equal. When you follow the ELQ, these will always be equal. Part D asks, well, what if our cost drivers change? What if the cost of carrying inventory gets more expensive? So instead of $75, it becomes $84. Well, what you should do then is recalculate your order quantity. If the cost drivers change, your order quantity needs to change. You need to go redo it, where in this case, rather than it being $75 to carry a bag, it's now $84. If you do that, you get a new order quantity. You calculate the cost of holding and carrying this cost, which is going to be more than this one. The reason is because our cost went up. So the total annual cost goes up by $79. That's the difference of the current and potentially if the cost changes of carrying inventory. Problem 21 is a reorder point model when we have variability in lead time and demand potentially. So they tell us that we used on average 21 gallons per week. However, there's variability so that we have the standard deviation is 3.5 gallons per week. We want to have a service level of 90%, which means that we need to use a Z score of 1.28. The lead time, they tell us, is 2 days, and you can want to do this in weeks so that all these are apples to apples. Since these are gallons per week, now we've got this lead time in weeks, which is 2 days. They say that the lead time is exactly that, or they say the lead time is 2 days. So what that means to me is that there's no variability. The standard deviation of lead time is 0. So the numbers that we need for our formula is those 5. Those are the things that go into the input. The first thing that I calculated was the reorder point. If we had no variability, if this was 0 and this was 0, then our reorder point is just our lead time multiplied by our demand rate. 6 gallons. So when we hit 6 gallons. However, we do have variability on demand. So now we have to add safety stock. The safety stock formula is Z times the square root of LT times the sigma of D squared plus the lead time squared multiplied by the standard deviation of LT, and this all should be squared. Now it happens to be 0, so it doesn't make any difference. But so the safety stock is 2.4 gallons. Safety stock is inventory you have to carry because we have uncertainty on demand or uncertainty on our lead time. So that is a consequence of variability in the system. So it's a layer of inventory we have to add. So our reorder point is no longer 6, it is this plus this, so our reorder point is 8.4 gallons. We now carry a layer of 2.4 gallons. It's a buffer to prevent against uncertainty in lead time and demand. The days of supply is just taking our reorder point and dividing by, in this case, the demand rate in a day basis. So we take the 21 gallons per week divided by 7, or 3 gallons per day. So we take this, divide by that, and so on average, from our reorder point, we have between 2 and 3 days of inventory available. Problem 36 we did in class. This is a single period model where we kind of get one shot to order things on a daily basis. We order fresh seafood. It costs us $4.20. These are all dollar amounts. We sell it for $5.70 a pound. Anything at the end of the day, we can scrap it or salvage it for $2.40 a pound. So we need to calculate the two cost drivers, the cost of being short. So these are also dollar amounts. This is what it costs you per pound for every pound that you don't have. This is the cost of having too much. The cost of having too much is the unit cost minus the salvage value. The cost of being short is the selling price minus the unit cost. From these, we can calculate the optimal service level. So this says that you should target to have a service level of 45%. It's the cost of being short divided by the cost of being short plus the cost of excess in the denominator. They tell us demand is normal with the mean of 80 pounds and a standard deviation of 10 pounds. Based on that and a normal distribution, and we need to have a service level of 45%, we could calculate the optimal order quantity using the norm.inv function. Our first input is our service level, and then we put in the mean, the standard deviation, and it tells us about 79 pounds. Okay, that's the inventory homework.